Check, check. All right, what's up, Black Hat? It's probably no real surprise that my slides didn't make the Black Hat book this year. I was figuring that would have made a good centerfold, huh? But no matter. Well, that was actually my first thing that came to mind when I thought about kernel exploits in assembly language. Was a half-naked girl with an EI logo tattooed on her bum. But that's my warped head, so whatever. I've got to go through like 75 minutes, so I'm not quite sure if I'm going to get all that done, but Mark Mayfrey's kindly offered to come up and do the robot dance while I beatbox, if I don't get the time in. Anyway, my name's Barnaby Jack. I'm a senior research engineer of EI Digital Security. I'll be speaking about remotely exploiting Windows kernel-based vulnerabilities. Anyway, that's enough eye candy for now. Did I hear an O? It's all right, there'll be more later, don't worry. All right, here's a quick overview I'll be talking about. I'm going to briefly mention the differences between Ring 3 and Ring 0, like user and kernel modes. I'll go over what's possible to do in the kernel, as far as what's possible and actually like reasonable for network shellcode. I'm going to look at a few published kernel vulnerabilities. There's been a couple coming out lately, like some serious ones. So, let's see. I'll talk about a few things that have to be taken into consideration when you're actually exploiting firewall drivers. And I'll talk about how to overcome those obstacles. Take a look behind the blue screen of death. Everyone's seen that, I'm sure. So we'll basically talk about how we can turn that nuisance into something useful. I'm going to talk about a technique that I've dubbed the clean return. And this is basically a way to return from any process or thread and have everything running as normal. This is after exploiting it. And this is obviously important when you're exploiting kernel vulnerabilities because you don't want to be there with a blue screen there. I'm going to very briefly talk about kernel heap overflows, and the only reason I'm doing this is because I saw this cat was talking about it in China, and so I thought I'd better throw something in. And to tell you the honest truth, I looked at this about 3 days ago, and so don't expect any rocket science, but I'll briefly talk about pool overflows. And then I'll talk about my kernel payloads. Now, the first one is a kernel loader, and what this allows you to do is use any userland shellcode and have it execute from the kernel. And the funny thing is you have ultimate power in the kernel, yet one of the handiest things is to drop back to user mode, so go figure. Next one will be the interrupt hooking keylogger, and this is basically a kernel mode keylogger which you can retrieve the captured keystrokes in real time from a remote system. And finally, my favorite demo, we're going to just completely kill the Windows OS entirely, and I'll explain more on that one a bit later. But if you fall asleep through most of it, I'd wake up for that one. All right, kernel and userland. Now, the Intel processor actually supports 4 rings, but the Intel processor, but NT OS decided to only use 2 of them, basically so they could maybe be run on architectures that don't support all privilege levels. User mode, Ring 3, that's where all your user programs and system subsystems run, and user code's pageable, can be context switched. By design, a user mode process cannot actually switch privilege levels arbitrarily. But this is where the native API comes in. I'll talk about that a little bit later. And obviously, this has been circumvented many times, and if you want proof of that, I'll check out some of Derek Soder's advisories on the EI page. They're completely sick. Kernel mode, Ring 0. Yeah, full system privileges can run anything you want, access the privileged instructions, and examples of what run in there is like your HAL, device drivers, I/O, memory management. This all runs in Ring 0. What can we do in the kernel? Pretty much anything you please, you know. You got absolute power. You're limitless to what you can do. Rootkit's a big time these days, so I mean you could install a rootkit without ever touching the disk. Let's see. Intrusion detection systems will set up kernel hooks. These could be subverted easily. You could access, patch the memory of any process or module, whether that be kernel or userland. And I'll be making use of that when I talk about the kernel keylogger, actually, because we're going to be patching some kernel code locations with that one. High processors, ports. I mean, that's going to make exploitation even harder to detect. I think Jamie's actually speaking about kernel invisibility right now, in fact. So actually, I appreciate you all coming out here because he's probably doing a pretty decent talk. Actually, they're releasing their book this year, which I definitely recommend getting a hold of, so it's pretty cool. Execute code from the kernel loader, and I'll talk about that one too. These are just a few examples. Basically, anything you can imagine is possible because, I mean, you have absolutely no restrictions. You're not constrained by the user land. So, a few published vulnerabilities. We released a bunch in Symantec's firewall, and so we went on their Christmas card list that year, I'll tell you. What else? There was the another Black Ice one. A lot of firewall ones. There was the SMB client transaction that was duly found by Dave Vitale and EI. Let's see. The flaw in the TCP/IP stack found by Neil Mehta, which is a great find by him. And most recently, there was the SMB flaw found by Qualys, who were kind enough not to give any details whatsoever. But it's amazing what you can do with a disassembler and a Microsoft patch these days. So here's a quick hint. SRV SMB transaction, max parameter count, max data count. Look it up. All right, so the exploit I'm going to be using for my payload today is one of the Symantec ones we found. It's an older vulnerability, but sorry, I'm not dropping any 0-day today. But I picked this one because it's in a firewall product. It's a standard kernel vulnerability. It could be exploited over a broadcast address. And I think it's kind of cool to actually break into somewhere through the very mechanism that's designed to protect the system, you know? All right. So yeah, actually the flaw was in DNS processing. And the cool thing, because due to another implementation flaw, you could exploit this with all port filtering, like the firewall at its maximum settings, and you could do it over broadcast address, so I thought it was dope. Did anyone see that? Those are my Fight Club-esque subliminal messages. All right. The native API. When you're writing kernel mode shellcode, you basically just got to forget about the user API entirely. You're just going to be only using kernel functions. Now, the native API actually exists as a somewhat safe way for user mode programs to call into kernel functions. What they do is, these are from the user API, you call through NTDLL, and it offers kind of a wrapper into the kernel. Basically, these wrappers will just load a register with a syscall ID. In Windows 2000, they'll execute interrupt TOE. And actually, in XP, they've crossed the more logical sysenter and sysexit instruction pair for doing that. Let's see. Actually, did anyone catch Brian and Derek's talk on the Bootroot project this morning? Sick, man. Big up then. Oh, hats off to Derek Soder again. I should have mentioned that earlier, but he rocks. All right, some considerations when exploiting firewalls. See, now a big problem is the firewall's going to have to process all incoming packets. So when we exploit this, we're going to lose all network communication. So we're going to need a way to get around that. And that's where I'll talk about the clean return a little bit later. Because obviously it's not a lot of fun to be had when you execute it and you can't access the system, you know. There's a few options here. You could try and directly unload the driver by calling a ZW unload driver, or just calling the unload routine itself. Just try and detach or delete the devices, send the IOCTL from userland, or unregister the Endless packet handler. And now, to be perfectly honest with you, none of those actually really work. That was just kind of theory. But there is one thing that does work, and that's returning cleanly. It's a surefire way to have the thread execute with no ill damage. So, I mean, you can just exploit the system over and over and over and over again. What that involves is sending an exploit, exploiting the system, and then returning into a previous stack frame. And I'll get into that a little bit. Let's see. All right, behind the blue screen. No doubt everyone's run into that. But what exactly goes on? I mean, this is how the kernel exception handling works. When exception is triggered, it can do a number of things. It can be passed off the KI dispatch exception, and the bug check will be called from within that routine. Now, KI bug check X is what drops you the blue screen, or all the code involved is within that function. Or the exception can actually be passed off to the trap handler, which goes through the IDT, and the bug check can be called from there. Now, when an exception is thrown, the kernel does gain control by various entries in the IDT, which are known as the trap handlers. That's the first level trap handler. So the trap handler can deal with the exception or locate a handler to pass down to, or if it can't be handled, it'll directly call KE bug check. When it calls that, then you get the blue screen. Softdice is probably my favorite debugger, but WinDebug is excellent for like memory dump analysis and whatnot, because it's got great structure recognition. So basically, if we want to do anything useful, we're going to need to know where the exception happened and get like register states and everything you need to exploit it, you know. So to do that, we're going to need to retrieve the trap frame from the time of exception. So you can load your memory dump on WinDebug. Let's see. And by typing KV, you're going to get like the complete stack trace there. And you can see that KE bug check was called from the KI trap OE, which is the trap handler, and it trap frame 8054199C. So then you just simply type .trap and the address of the trap handler, and it's going to give you the register states. You see EIP was 41414141, so I mean that's obviously they got owned. And by dumping ESP, you see that all our data is in the ESP register. And from there on out, you pretty much just go exploiting a kernel bug like you would a user mode bug. So yeah, we need to redirect execution. I mean, anyone who's written an exploit, this is standard fare for them. Basically, the data's in ESP, so the only one difference is we're going to need to choose an address in the kernel which is going to be static. So you're going to want to pick like NTOS kernel or maybe HAL, and you just want to find like a push ESP ret, jump ESP, anything like that. Anything that's going to return you to ESP there. Now, the clean return. So as I was saying earlier, we need a way to safely continue execution without disrupting the current thread. And what we do is we're going to send a minimum amount of data, enough to actually cause a stack overwrite and overwrite EIP. And then we're going to put a small amount of code in there, which is actually going to patch the driver itself. So it will patch it to execute certain flagged packets that come in. And after that, it's going to return to a previous stack frame, which is going to return to the TDI driver. So that way you can just exploit over and over and over again. And the cool thing about this can be used for like any exploit. It doesn't have to be kernel, like user mode or kernel. And yeah, it's basically dope. So what I did, I patched the SIM DNS driver, which is the driver that's handling all the DNS requests, which is where the vulnerability is. And I patched that routine to just execute certain DNS packets that come in. All right. So when we actually send the vulnerability, we've got about 300. It's actually kind of hard to explain by slides, but I'll try. We've got about 300 bytes of space before we return into the SIM-TDI driver. So basically what I do is I go and exploit it. I have my patch code, and then I'll just retrieve that previous stack frame, which is like at ESP plus X130, and just return into that. I was actually going to run through this in the debugger, but yeah, I was a little hungover this morning and actually accidentally snapshotted at the wrong point, so what can you do? All right, here's a very brief overview of kernel heap overflows. Now, this is completely brief, and in fact, I did this like yesterday, so don't expect any rocket science at all. I just ran a quick test demo, allocating a buffer with xallocate pool, overriding that buffer, and then freeing it. Now, the good news is that kernel pool overflows, from what I see, can be exploited just like userland vulnerabilities. You still have like where you can control the data and overwrite another register with like data of your choosing, you know. But well, the bad news that I noticed on XPSP2, it's going to actually crash with an invalid pool header. But I haven't looked too much into that. But you know what? I'm just going to quickly plug something. We have a newsletter called Vice, which is basically our research newsletter with EI, where we it's just kind of a research brain dump. So anything we're like currently researching and just want to tell people about, we'll dump it in there. So I'll look more into this and I'll put it in that newsletter. So I suggest you sign up for that. It's pretty dope. So now the most important thing is actually gaining control. And there's a perfect routine to overwrite, which is in the KI dispatch exception. Because obviously you're going to cause an exception, and it's going to go to this routine. So you can overwrite KA debug routine with your code, well, like a pointer to your code, and you're pretty much sweet. But see, well, actually, there's one problem here. The KI dispatch exception doesn't get called from all exception types. And that way it can go directly to the trap handler, and it will just call KE bug check. But there's actually a function KE bug check you can overwrite to. But the thing is, that's probably going to make it a little bit harder to get back to your code. But yeah. I'll try and find some proof of concept and publish this stuff. All right, so the first payload I'm going to talk about is the kernel loader. And what this shellcode allows you to do is plug in any userland shellcode and have it execute from the kernel. So, I mean, it's funny, you've got all that power at your disposal, but, you know, the handiest capabilities just to go back to userland, you know? Go figure. Anyway, any userland code can be plugged in, and the load is pretty small. It's like a little over 100 bytes. So you can execute your remote shell or a user add or any, like, shellcode that you'd normally use in userland. So you can just use with that. See that one? It's my cheap attempts at mind control. I hope it's working. All right, so for us to do anything useful, we're going to need to retrieve the NTOS kernel base. And we want to keep our shellcode generic, so we're going to have to avoid using hard-coded offsets. And a quick and easy way to get the base address is to retrieve an entry from the IDT and basically just scan down until we reach the executable signature. The thing is, you don't actually have to retrieve a valid IDT entry. You can just like grab the high word and let it safely go from 0 to 65535, and it's going to safely stay in NTOS kernel memory. There's a couple of ways to get the IDT base. You can, most common way is just use the SIDT instruction, but you can also just reference a memory address FFDFF038, and it'll shave off a small number of bytes. And that's obviously useful when you're writing shellcode because size is obviously a factor. Retrieving procedure addresses. This is simple stuff. This is like a standard get proc address implementation. And so, yeah, it's just a matter of passing the portable executable table, the export table with the portable executable, I'm sorry. The one difference in this implementation is it's just like the 2-byte hashes I use instead of function strings. And I just do that by using like a XOR rotate just to get the hashes. And just generally because like function strings take up like an excessive amount of space in shellcode, so I may as well like wipe that out, you know. And then I just fill a table with the procedure addresses. Protecting the stack. Now, this isn't really necessary when you're doing the clean return because yeah, it just don't matter. But if you're like, for some reason you can't do that, the stack's going to get corrupted when calling certain routines. Particularly when you attempt to drop the interrupt request level, that basically just wipes out your stack completely. So to get around that, just simply allocate some more memory, copy your following shellcode in there, and just jump to that. All right. Speaking of the interrupt request level, when we break in, we're actually running at the dispatch level, which is like reserved for like DPCs and thread schedulers and whatnot. To actually successfully call some of the functions we need, we're going to need to drop it down to the passive level. So, I mean, that's a simple matter of calling the HEL exported function K lower IRQL and just pass 0, which is passive as a parameter, and that will drop it down. So we need to map in our userland shellcode. We're going to need to map this. I'm going to be like hooking into the LSASS process, so I'm going to use that as my way to execute my system shell. Now, there's a couple of ways. Oh shit, am I looking at the right thing? Oh, here we go. Okay. So we need a process running in the system context to spawn our thread. So we can. What I'm going to do is just traverse all the user processes and just go through the eProcess block. So every process has an eProcess structure. Then I'll pass eProcess and active process links, and that way we can just loop through all running processes in the system. Once we like hook on to the LSASS one, then I just like save that structure, compare the module name to find the LSASS, and just save the LSASS process. Going to use that later. Now we need to map in our Ring 3 shellcode. Now, there's a couple of ways to do this. Originally, I was actually sending it into the PEB, but there's actually a better option for that. the better option is to copy it into, there's a block of memory which is kernel, like it's shared between kernel and userland. I think it's called shared user data or something. Anyway, this memory is like mapped at one location in the kernel. It's also mapped at a different address in userland. So we can like copy our shellcode to that, and then any userland process can access that memory. So, I mean, that saves me having to actually attach to the LSASS process, write it to its PEB. We can just copy that, and then anything can access it, you know? I just like seeing it maybe like 1,000 bytes after that, because, I mean, maybe I'm overwriting something important there, so I just make sure I'm not doing that. Now, to actually contact userland, I actually issue an APC. Asynchronous procedure calls a function that's going to execute synchronously in the context of a chosen thread. They can be issued from the kernel or the userland. Now, every thread has an APC queue. In our case, we're going to be firing one off the LSASS thread. Now, when you queue an APC to a thread, interrupts issued and the thread scheduled, and the APC function will be executed. Now, for the APC to actually execute, you need to find a thread in what's called an alertable wait state. So you can actually manually set the thread to be alertable, or you can just like loop through and find a thread that's actually already in an alertable wait state. And from like, okay, if thread enters an alertable wait state after calling like sleepx, signal object and wait, message wait for multiple objects, etc., etc. And from my experience, there's always like a couple of threads in one of these delay execution states. So I took that path. All right, to actually issue the APC. So we already have the pointer to the LSASS E process, and we need to find a thread that's going to meet our requirements. So we can get the E-thread structure via the E process. Once we've got a pointer to that structure, basically just loop through all the threads until we find a thread which is in an alertable wait state. And then we just need to initialize and queue the APC. And we do this by passing the K-thread structure, our shellcode, which is in shared user data, and a kernel callback function. And then we just pass the APC handle to KE insert QAPC, and it's as simple as that. Now here's the bummer. My first demo doesn't actually work, because I was screwing around with it earlier, and it buggered out. But the good thing is this is the lamest of all the demos, so you know, just use your imagination. You can probably think up something that looked cool, so there you go. But anyway, all I was going to do was drop a remote shell, and I'd fiddle around and blah, blah, blah. All right, so I'll talk about something better now anyway. The kernel keylogger. This operates entirely in the kernel. I think, actually, this is a lot cooler, I think. It will capture all keystrokes, and the keystrokes can be retrieved by a remote system through ICMP requests. And you can do this pretty much in real time as well. This demo actually works, so I'll show you that one soon. And the way I've gone about this isn't exactly standard. This is shellcode after all, so like trying to create like a full-fledged communications tunnel and a keyboard filter and whatnot, it's going to be a bit of a bastard. So instead, I sort of kicked it back a little bit old school and went back to like the DOS TSR days, and probably people remember the game trainers and the little hotkey pop-ups there, you know. So they all work by directly hooking the keyboard interrupts, and that's exactly what I'm going to do. And so we also need a way to actually retrieve these keystrokes remotely. So as I said, I'm not going to be creating a full communications tunnel. So instead I cheat again and patch the TCP IP driver, and I'll patch the send echo function. So when we ping it, it can return all our keystrokes to us. Now, we need a way to get the interrupt vector from the IRQ. See, unfortunately, the interrupt vector is not always going to be static. The keyboard IRQ is IRQ1, and so we need to find, like, actually, I think on like Win2K SP0, I think it's all static, like IRQ1 is x31, IRQ2, x32, etc., etc. But the good thing is there's actually a IRQ to vector table in the HAL memory address space. And so basically you just scan for that D word 414113 3Ds, or whatever it says, in the HAL memory space. And this D word marks the beginning of the IRQL to TPR translation table. And this neighbors the vector to IRQ table. So we can just retrieve that vector offset by adding 1C to the IRQ table, and we just simply retrieve the vector that corresponds to IRQ. As I was saying, on earlier service packs it doesn't exist, but they're all static. So in the event the table's not found, I just use like the static vector of 31 for the keyboard. We're going to be overriding kernel code, so we need to... I use SoftIce, and I realized that it actually disables all memory protection when I found out when I tried to exploit something that wasn't running debugger. So, so we need to remove the memory protection. This is pretty simple. We just need to disable the write protect bit in CR0, overwrite the code we need, and then just re-enable the bit. All right, so I'm going to be overriding the IDT entry, the keyboard IDT entry with our own custom keyboard handler. So we get the base of the IDT again, SIDT, or referencing that memory address from earlier. To retrieve a vector entry, it's just IDT base plus vector times 8. We'll just save the address of the previous handler, overwrite the IDT with our own, and yeah, I'll talk about what my actual handler does in a couple of minutes. So we've got to locate the image base of the TCP/IP driver. We can do this by passing the PS loaded module list. Unfortunately, this isn't actually publicly exported, but we can retrieve the offset of this by passing through a function that is publicly exported and references the offset, like get system routine address. That's what I'll be using. It's actually the format of the module list structure. We just basically loop through, compare the TCP/IP string with the module name, and once we find it, we'll just retrieve the base address from the structure. And there you go. All right, so we're going to be patching the ICMP echo handler. So this is basically a disassembly of the send echo routine, and right here is getting the buffer into EAX. So we're just going to patch that to use the buffer that we created for our keyboard handler instead. So basically now, anytime an ICMP echo request is received from the system, it's going to reply with our keystroke buffer instead. Now, our custom handler. This one executes before the original keyboard handler. Here's how it works. We basically just directly retrieve the scan codes from the keyboard port, which is OX60. We allocate a buffer to store all the scan codes. Now, this is the same buffer that's going to be referenced in the TCP/IP driver now, and then we just circulate every 1024 key presses. There's no scan code translation or removal of any scan code, so we just capture everything in the raw, and that way you'll be able to receive all key combinations, you know? All right, let me demo this one. This one actually does work. Actually, let me just review on that real quick. I always want to beatbox on stage. Sounds good. All right. What's that, bro? Oh, was that too small? You still get the idea. All right, so now I'm just going to send the kernel payload, which is going to do the whole keyboard thing, and you'll be able to remotely retrieve keystrokes. So hopefully this works. All right, now Derek Soda wrote a cool little tool which does all the ping requests and returns the keystrokes. So you can pretty much do that in real time. Let's see. See, even does the caps locks. All right, that one worked. Now, this is my favorite demonstration. This is where we just basically kill Windows entirely. Now, a friend of mine called Derek's and Ryan's, they did something in a similar vein, but they went back to real mode and... You didn't do that? Okay. Well, I actually missed their talk because I was asleep, but I was hoping that's what they did. You tried, it didn't work? Damn, the demo gods. Okay, well anyway. I used to always get a kick out of like those old school demos and intros, you know, like those old Future Crew demos, Second Reality and whatnot. Anyway, like the NTVDM hardly runs any of these. So what we thought would be cool was to switch from kernel mode back to real mode and execute like a nifty little intro in the bootloader memory region. Now, as far as real-world purpose goes for this, I'm still trying to decide that one, but maybe if you want to run Second Reality, there you go. Did anyone ever see that demo? Wasn't that the sickest, bro? I still think that's the greatest demo. Actually, our original idea for this was a little bit different, because the vulnerability I'm using here can be sent to a broadcast address. So what we thought would be pretty cool would be to like execute a Space Invaders game. And this cat actually wrote up a little Space Invaders game and everything. And so I thought, like, you send this one packet, and then like the whole subnet's playing Space Invaders. And then like, if you're like good enough to get like the high score, then maybe you get back to protected mode. If not, blue screen. Anyway, we never really got too far with that idea, but I think you'll dig this one anyway. All right. Now this is the boring part here. So these are the steps required to switch from the kernel to real mode. We're going to need to acquire the display from Windows. This is done by calling a couple of HAL exported functions. Oh no, actually no, they're exported from Intel's kernel, my bad. We're going to have to map in some physical memory so we can actually copy our code to the bootloader region. We have to transfer control to an identity mapped region. We're going to have to clear the paging bit in the control register 0 and write 0 to control register 3 to flush the TLB. We'll jump to a 64K limit segment, point our interrupt table somewhere in the first page, clear the PE bit in CR0, far jump to a 16-bit address, load up segment registers. Now, the thing is, we're going to need to, the slides will be up. So we're going to actually need to prevent any interruptions. And we do this by calling KE raise IRQL, and we raise it up to high level. So first we need to acquire the display, and we do that by calling the MVV reset display and acquire display ownership from the Intel kernel. And that way, once we've got the display, then when we do go back to real mode, we can use the BIOS interrupts to change video modes. Now, to map in our memory, see, we're going to be copying into the bootloader region. Now, a quick way to actually map in our memory is to change the page size bit in the PDE, which is like, the first one's at C0300000, and we just set page size to bit 1, and that will like give us like a 4 megabyte page, so we can just copy our crap in there. So we copy the mode switch code into the low memory region. It's going to execute 16-bit protected mode. We copy our payload into the bootloader region, execute LIDT to point our interrupt table back into the first megabyte. Protected mode code sets up the segment registers, points the stack into low memory area, points the ID to the first page, jumps to the identity map address. Now, the payload itself. Did I just skip one? Oh, yeah, there we go. So the mode switch code sets up our stack segment, loads of segment registers, write 0 to CR3. You know, I'm going to be giving away all this code, and I'll just put it on the EI website, because it's kind of hard to explain this without just seeing the code. And I want to get to the demo because I'm getting all giddy about it. All right, so the payload itself. This is like, originally was like a little 256-byte intro written by this European cat called LoveC. And my boy Derek added some like nifty EI effects to it and like went old school, and I think it's totally sick. So here we go. Please work. Let's go full screen. Isn't that the shit? And Vita's back. All right, any questions? No? All right, thank you guys.